Hey everyone, this is Chapter 10 Review. In this video, we're going to talk about rotational motion. This will include the kinematic equations, and then moment of inertia, Newton's second law, rotational kinetic energy, and angular momentum. Let's start with rotational motion. When an object is rotating about a fixed point, then the points on that object, such as points A and B here, are going to move a certain angle delta theta as they go from those points to the corresponding point on this line on the right here. That angle theta that they're moving by, that's the displacement. It's the angular displacement. And we use the unit radian to describe it. No matter where the point is, they're all going to have the same angular velocity. Angular velocity uses omega, and the average angular velocity equals this angular displacement over the time. It's measured in radians per second. So since they're both points A and point B are moving that angle in the same amount of time, they have the same angular velocity. And then angular acceleration is defined as the change in angular speed divided by time. It's measured in radians per second squared. So likewise, all the points on the object have the same angular acceleration as they're rotating. Now, these are vectors, so they do have a direction. To specify the direction, if an object is moving clockwise, we use a negative sign. And then if the object is moving counterclockwise, we use a positive sign for the displacement, velocity, and acceleration. So a key thing here is that every point on a rotating object has the same angular motion, but does not have the same linear motion. If you look at points A and B here, as the object is rotating, points A and B are moving linearly at any time. Point A is going to move faster as far as its linear motion because if it does a full rotation, it has to travel the full circumference of the circle, while point B here would have a smaller circumference to travel. Let's look at the kinematic equations. We learned these when we were talking about linear motion, and this is what they look like. We had 4 of them. We needed 3 out of these 5 variables in order to solve problems. So it's the same thing when we're dealing with rotational quantities. We need 3 out of the 5 variables. This time the variables are angular displacement, initial and final angular velocity, angular acceleration, and time. If we look at the kinematic equations for angular motion, they look just like the linear ones, but the v is replaced by omega, whether it's v initial or v final. The a is replaced by alpha, the t stays the same, and the delta x is replaced by a delta theta. Sometimes when you are solving problems, you are not given all linear quantities or all angular quantities, and you have to convert from one to the other. To do that, you're going to use these 2 conversion equations, v equals r omega and a equals r alpha. This allows you to convert a linear quantity to an angular one and vice versa, so that you can get the 3 out of 5 variables that you need in order to solve a problem. Let's do an example. A merry-go-round rotates at 5 radians per second and comes to rest in 1 minute. How many revolutions does it make while it comes to a stop? So first we want to identify 3 out of the 5 given variables and our unknown variable. We're rotating at 5 radians per second. That's the initial angular speed. And then it comes to rest. So that's the final angular speed is going to be 0. It takes 1 minute. That's going to be the time, but we're going to go ahead and convert it to seconds since the units for angular speed are radians per second. So we have our 3 given variables. Now the unknown variables is how many revolutions does it come to a stop? Whenever you see revolution, you want to think of an angle because revolution is a unit for the angular displacement. So now we identify a relevant equation that has these 4 variables. In this case, it's going to be the third equation. We're going to solve for the unknown variable. In this case, delta theta is already solved for on the left, so we can move on to our last step, which is to plug in the values. Note that when I'm talking about initial angular quantities, I can use I or 0. They're interchangeable. So let's plug in our values. 1/2 times 5 radians per second plus 0 times 60. That's going to give us 150 radians. But it's asking about revolutions, so we need to convert. To convert from radians to revolutions, we know that there are 2 pi radians in 1 revolution. So we're going to write revolutions on top and 2 pi radians on the bottom so that we can cancel out the radians and be left with revolutions. We're going to get 23.9 revolutions as our final answer. Let's move on to the moment of inertia. The moment of inertia of an object depends on its mass and its distribution. The higher the mass, the higher the moment of inertia. As far as the distribution, the further that the mass is from the axis of rotation, the higher the moment of inertia. If you have a point mass, the moment of inertia is defined as the sum of mr squared. How many ever masses you have multiplied by their distance squared from the axis of rotation. The unit for moment of inertia is kilograms times meters per second. Note that when an object has a small moment of inertia, it's easy to rotate. When it has a large moment of inertia, it's harder to rotate. Now, we're not always going to have point masses. Sometimes we're going to have objects with a defined shape and volume, such as one of these 4 objects over here. So which one of these objects has the smallest moment of inertia about its central axis? Because whenever we are defining the moment of inertia of something, we need to know the axis about which it's rotating. The axis is going to affect the rotation because it's going to affect how the mass is distributed about that axis. So in this case, if we're rotating about the central axis, we can see that the solid sphere has the smallest moment of inertia. That means it's the easiest to rotate. Let's look at Newton's second law for rotational motion. Basically, it tells us that torque causes angular acceleration. Angular acceleration alpha equals sum of torques over the moment of inertia. This is very similar to the Newton's second law that we know and love. The acceleration equals sum of force over mass. So the smaller the moment of inertia, the bigger the angular acceleration. That's why something with a small moment of inertia is easier to rotate. Let's look at an example. What is the angular acceleration of this disk? Let's assume this is a solid disk. That means that the moment of inertia from the previous chart is 1/2 mr squared. Now, angular acceleration is given as a sum of torques over I. The torque is due to this force, which is called 2F, and it's acting at a distance r from the axis of rotation, which we're assuming is at the center. So the torque is going to be just a force times the distance, 2F times r. And then the moment of inertia is 1/2 mr squared. We can cancel out one of the r's and we can simplify the numbers. We're going to get 4F over mr. So if we had values, we could plug them in to get the angular acceleration of this angular disk. Next is rotational kinetic energy. Whenever an object is rotating, it's going to have this type of energy due to its rotation. The rotational kinetic energy is given by 1/2 I omega squared. The unit is joules, just like all the other types of energies that we have talked about. Let's look at an example. Which object has more energy when rotating at the same angular speed? So if both of these objects have the same mass and they have the same radius, then the one that has the most energy is going to be the one that has the biggest moment of inertia because they have the same angular speed. We saw in the chart that was given us the moment of inertia for a hoop or a hollow cylinder, the moment of inertia is mr squared, while for a solid disk, it's 1/2 mr squared. Therefore, the hoop is going to have more rotational energy because it has a bigger moment of inertia. Let's look at conservation of mechanical energy. When we have objects that are rolling, the sum of the initial kinetic and potential energy equals the sum of the final kinetic and potential energy. When we're rolling, then we have 2 types of kinetic energies. We have the regular linear kinetic energy, 1/2 mv squared. And then we have the rotational kinetic energy 1/2 I omega squared. So we have the linear one due to the speed as it's moving down. We can think of the center of mass having that linear speed all the way down. And then it has this rotational energy because it's rotating. And then we also have the gravitational potential energy, mgy. We have the same quantities for final. These are all supposed to be F here. That is a typo. So let's take a look at an example. All of these three shapes have the same mass and the same radius. Which one wins the race? We learned that the object with the smaller moment of inertia is going to be easier to rotate. So this gives us an idea that the sphere is going to win the race because it does have the smallest moment of inertia, which was 2/5 mr squared. If we look at a conservation of energy equation, and assuming they're all starting from rest, they all would have 0 kinetic energy to begin with. They all would have gravitational potential energy. They all have the same mass, they all have the same potential energy to begin with. So then let's look at their final energies. They get to the bottom, so they have no height. So their potential energy is converted to kinetic energy. So we can see here that the one with the smallest moment of inertia is going to have a greater angular speed. And let's look at angular momentum. It's defined as the product of the moment of inertia and the angular speed. The unit is kilograms times meters per second for the moment of inertia, and then divided by second, that comes from the angular speed. When an object is rotating, it has angular momentum. When there's no net external torque on the object, then we have conservation of angular momentum. For us, we know that we're going to be able to use this equation whenever an object is rotating and the distribution of its mass is changing and it's not due to some external factor. In that case, we have the initial angular momentum equals the final angular momentum. Let's take a look at this example. What happens to the boy's angular momentum when he extends his arms outward? So this would be a perfect case of conservation of angular momentum because there's no net external torque causing this distribution of mass. So that means the angular momentum is not changing. It's going to stay the same. However, if the question had asked about what happens to the angular speed, well, in that case, because we are increasing the moment of inertia when we are extending the arms out, that means the angular speed would become less. That's it for this review video.